Good morning, and today we continue the lecture on multi-thread and parallel programming. So yesterday we were talking about condition variables and the fact that condition variables are used to synchronize threads. So the typical usage is to pair them with a mutex. And so basically the idea is that you go with a lock, then you check a condition inside a while, and if the condition is verified, you are going to block. And as I said, you can only construct condition variables, you cannot copy or move. And you can wait for some time or until a certain point in time, so very similar to the lock. You can notify threads that are blocked in the queue, or you can notify all threads that are now in the queue. And you have also a shortcut for the while, which while ulock pred, and actually this should be a not. So while not pred, wait ulock. The while is necessary, and we explained why, because of these spurious wake-ups, and because in the case you have multiple threads arriving, there can be some problems. So some thread can actually surpass the other thread, and so you can have inconsistency. So in general, it's always better to, when you wake up, to check again the predicate, the condition, before continuing accessing the critical section. Okay, so we have done some exercise. We have seen a simple FIFO mailbox with blocking on the product and on the consumer, and we have seen a synchronization barrier. So let's go back to this example now and see what's going on with the synchronization barrier. Meanwhile, I uploaded the exercises into Didactive. So if you go into the material documents section and you go into the zip subsection, you find parallel examples. So I invite you to download it, because we are going to actually do a little bit of exercise with that. Okay, so parallel examples is a zip file, and you can download and see and unzip and see what you need to do. Okay. Okay, so let's go back and look at the example with our barrier. Okay, so basically the idea is, as I said, that I want to all the thread to execute in steps. So basically everybody is going to stop at the very beginning, then print something on the screen. Then in this case, just to show how it works, I added a little bit of delay, 100 milliseconds, and then it stops again. And threads, I start them all, and then for 10 times I continue to start all of them. So the idea is that everybody executes in steps. Okay, to avoid the output to be mangled, I define this function that I call unique printf. So you remember last time we have seen how to write a printf with variadic templates. And so this is the safe print we have already seen last time, and the safe printf, which just works on the standard cout, And then I defined a unique printf, which before starting it takes a lock. Now this lock must be global and unique for everybody. So I define the lock in var printf. So in var printf there is this function that I call lock printf, which returns a unique lock. So there is a static variable m, which is a mutex. You remember the meaning of static variables. A static variable means it's not a local variable, in the sense that it's not created and destroyed every time the function is called, but it's created the first time the function is called, and then it stays there, like it were a global variable. So basically, the first time I call unique lock, the mutex is created, and then I return a unique lock on this mutex. So this is going to be an object, and this return will move the object, so the ownership of this lock, into the caller. Here is the caller. So the caller stores the object into LCK, the local variable. And LCK is going to be destroyed, and so release ownership on the mutex when this function terminates. So basically, safe printf is executed in mutual exclusion with every other unique printf. Okay, did you understand this? So again, unique lock defines a mutex as a static variable. So that means that this is like it were a global variable. The only difference is this is created the first time lock printf is called. Then this lock printf is going to return an object that takes the ownership on the mutex, so locks the mutex. Now you cannot copy these guards, but you can move them, and so basically you can move this object unique lock into the caller, so here. So this is copied into variable SCK, which retains the ownership on the mutex. Now safe printf is executed in mutual exclusion. When safe printf terminates, we just go back to the caller by releasing the lock on the mutex. Okay. So if we go to where we call it, so this every thread will call unique printf, and so we'll execute the code which prints this string in mutual exclusion with every other thread. And that's it. Let's see also how I created the threads. So I just called the function transform on this which are just integer, every time creating a thread by passing the corresponding index and a reference to the synchronization barrier, which are exactly the arguments of function body, an index and a reference to a synchronization barrier. Remember the reference here, otherwise we are passing a copy, something that we do not want. Then we start all threads the first time, and then we start them 10 more times. Finally, we wait for all of them to finish by calling the join, and we really finish with by printing end. We compile everything. Okay, so with respect to the execution of yesterday, you can see that the output is not mangled anymore, but still everything is done in order, so 5, 6, 7, 8. However, within a certain step, of course, the threads execute in random order. Okay, so for example, this order is actually different from this other one. 3 and 1 are different, and also its order is different. So every time is a slightly different order. Okay, so this is an example. Let's look now at okay, so now let's look at the implementation of this barrier again. So this is the synchronization barrier implemented yesterday, and I did a little bit of modification. I modified the sync so that now it returns a Boolean, and I modified start to accept a Boolean. So the idea is that I can use this interface. If I call start without anything, by default the parameter is true, and this means that I want them to continue. And so this true is returned by sync. If instead I want them to stop, I pass false as an argument, and this false is returned by sync, and this can be used by the threads as an indication that they should terminate. So it's a very protocol for communicating between manager and parallel threads. Okay, and so the implementation is very simple. There is a Boolean flag here, which is initialized to true, and if you go and look at the implementation, you will see that the sync will just return the value of the flag, which by default is true, and the start with set flag to the parameter which I just passed before notifying everybody. So before notifying everybody, everybody's logged here, I just change the flag so they will return the new flag. Okay? And that's it. Okay, so now we want to use this for implementing the problem we discussed yesterday. Look at this problem. Where did I put it? No, sorry, wrong. Show all bookmarks and sorted bookmarks. Okay, so here is it. We want to compute finite differences on a vector. So we have elements in a vector, and we want to implement this specific formula for each element. So the idea is to use many threads. So if we have 8 threads and 8 places, we are going to actually have one thread for every place that computes this formula. Okay? Otherwise, if we have a very long vector and less threads, we will just divide the vector in chunks of equal size. Every thread takes care of computing these formulas on its own chunk. Okay? The idea is that I do the computation on the vector and I put the results on another vector. And when I'm ready, I just communicate to the manager, and the manager will take the result, swap the two vectors, and continue executing on the next step. So at every step, we just compute this finite difference. So this formula is actually a sort of a formula that gives us a sort of heat diffusion algorithm. Okay, so basically it's like you have a long piece of metal, and you have initially one side is very hot, and then you observe as time goes by how the temperature is modified along the metal bar. So let's look at one implementation of this. I just did the implementation, and you can find in file parallelvector.cpp. So if you just downloaded the zip file from Didactive, you will find the code into parallel vector. Okay. Okay. So the idea is that the body represents the body of the threads. Okay. So it's going to use our barrier. So initially, it takes as parameters a reference to the barrier that you used for synchronizing the different steps. Then it takes as input a vector where the initial values are, and takes another vector where to put the results. And then it takes two indexes on these vectors, start and end, which represent the chunk, the portion of the vector on which it should operate. So it's quite simple. While I have to continue synchronization, so usually this returns true. So while true, it means the cycle continues until sync returns false. So I do a for cycle from start to end, and I compute R this formula, where coefficient is actually 2. So I just sum twice the current value plus the value at the right, and I divide by 3. If I am on the other side of the bar, so at the end of the bar, I do the same, but this time just summing the left part. And if I am in the middle, I just use the formula that you have seen on the webpage. Okay? So I continue to do this until there is something to do. When the work is finished, sync will return false, and then the thread just completes and terminates. Okay, by default, I'm going to use 20 threads. A metal bar of 20 elements, and I'm going to use a number of threads equal to the number of cores in my machine. So this function just returns the amount of concurrency, hardware concurrency in your processors. So in this case, I'm on a Dell laptop. I have a quad core, which is actually 8 level of parallelism, because every core has a hyperthreading level of 2. So in total, I have 8 virtual cores and 4 physical cores. So this is the main. I take arguments, minimum 2 arguments, and the first argument is the length of the simulation, so how many steps in the simulation. Then I take optionally the number of threads and the size of the metal bar. If I just printing the instructions on how to use it, otherwise I just take the simulation length as a first argument. If I have a second argument, I take the number of threads, and if I have a fourth argument, I take also the size of the metal bar. Okay. Then I size the two vectors vec and res equal to v sides, and by default they are initialized to 0. I also initialize the first element of the vector to 100. So it's like I have a very hot spot on one side. I want to see how this evolves with. Then I print the parameters with which I'm running everything. I prepare a synchronization barrier, and then for the chunks. So start is initially 0, end is a start plus v sides divided by n threads. And if I is the last thread, actually I put it equal to v sides. Okay, because if it's not equally divisible, then I'm going to make the last chunk a little bit larger. Okay, and then I create the threads and I put them into the vector by passing the function to execute, a reference to the synchronization barrier, a reference to the initial vector, a reference to the resulting vector, start and end. And then I put start equal to end and I continue. Okay, so this creates the chunk size. And okay, and then here finally I have the simulation. The threads have been created, so they are ready to start. So now for this I that goes from 0 to the simulation length, I start all threads. Then I wait for them to terminate the first step. When they terminate the first step, I swap the two vectors. Okay? And I continue like that for all the steps of the simulation. At the last step, I just say that they can terminate. So I do SB start false, and I wait for them to terminate. So I join all of them. Okay? So let's try to see how does it work with 20 elements. And so I compile, and I start executing it. So if I just run a parallel vector without any specific parameter, it asks at least for the simulation length. So I put like a very small number of elements and a very small number of steps, and I run it. Okay, sorry, the printing is not perfect, so. I didn't want to split, sorry. For some reason I got splitted. How do I split? Close active. Okay. So I don't know if you see, probably not, but it's just to give you an idea. Okay, so this is the result of the simulation. And I don't know, it's probably very little, so you cannot see. But at the very beginning, it starts with this, so 66, and then it continues to decreasing. And then finally, at the end, it's more or less uniform. Okay? So if you continue the number of steps, it will become more and more uniform. Okay, so for example, now here is converging to 5, and here we are still at 1.7, but if you run for, I don't know, 1000, at the end everything is equal to 3.85. Okay? Okay, but are we sure that this works? In other words, are we really making it faster than a single thread implementation? So what's your guess? Are we going faster with 8 threads or not? So please guess.
I don't know. It depends on how threads are handled.
Yeah, I mean, you see the code. You should have downloaded it, so you can see what happens. So what is your intuition? Is it going faster or not?
Yes. I hope yes.
So let's do. You can see how fast it goes by running the time command on the Unix. So I'm going to run a parallel vector on 1000, a little bit more, 10,000, okay? And the default is 8 threads and 20 elements in the vector. Okay, now sorry, I first compiled, so I removed the printing, so we are not influenced by the printing. Okay. Okay, so it takes a little bit more than 300 milliseconds. Let's run a little bit more, so 10 times more. So it takes a little bit more than 3 seconds. 3 seconds and 100 milliseconds. Now let's run that on one single thread. Well, it takes much less. It takes only 685 milliseconds. So one thread goes much faster than 8 threads. How can it happen? Do you have any idea?
The time for the synchronization.
So the time for the synchronization, it's actually quite important. Yes. So this is one reason. Synchronization is one reason. And there is another reason, and that has to do in part with how data is structured. So let's try to make the vector a little bit larger. So I'm going to take 100,000 elements in the vector. This means that every thread processes much more data. So with 20 elements in the vector, every thread was processing 2 or 3 multiplication and division before blocking. With 1,100 elements, each thread is now doing much more work. So basically, the ratio between synchronization and work to be done is now much higher, because every thread does a lot of work before synchronizing. So the step duration is larger. So now I'm doing 10,000 steps on a vector of 100,000 elements with 8 threads. It takes 2 seconds. Okay? So actually less than the 3 seconds on the previous case. Of course, here we had a little 10 times more steps, but also a lot of synchronization. Let's try now the same configuration with just one thread. Okay, so now it's a little bit better. One thread takes twice as 8 threads. So scalability is not very good, because perfect scalability, it should be multiplied by 8, right? Yeah. Instead here we are just multiplying by 2, so we are still not very good. But at least we have improved a lot. So this is just to try to make you understand that programming parallel code is not easy at all. And so I would like to show you also another example. And this other example is actually a simpler program in which we have no mutex and no synchronization. So we are just going to look at one other problem that has not to do with synchronization, but is quite a different thing. So in general, it's quite difficult to write parallel code because of the many sharing parts, many common resources in the hardware. So let's try to write a very simple parallel program, and let's see if we can make it fast. We want to compute how many elements in a matrix are odd. So odd is the contrary of even. That means it's not divisible by 2. So we have a matrix of integers. We want to check how many of the elements in the matrix are odd. So the sequential code would be something like this. We do 2 for cycles, and we check every element in the matrix, and if this is the modulo 2 is different than 0, then we increment one global variable odds. So very simple. And this actually is so simple that this code is very easy to parallelize, because what you need to do is to split the matrix into pieces of different sides and just let every thread that do the count independently. So we are going to do like this. There is no synchronization because we just start the thread, and the thread does all the computation and terminates. So no mutex, no condition variables, no anything. And we are going to work, every thread is going to work on its own data. So we prepare a vector of results equal to the number of threads. And then we create the threads by passing the body of the function to execute, start and end, as usually computed in some way, and a reference to the position in the result where the result should go. So the body goes from start to the end and puts the results into result, which is one element of this vector. And so the idea is very simple. 2 4 cycles, if the matrix is divisible by, so if the division by 2 is different from 0, then we increment result. That means we increment the position P into the vector. Okay? Okay, let's look at the code. So the file is called count matrix, and it's here I use an array. An array in C++11 is just a generalization of the C array. So it's a template. You specify the type, for example, integers, and the number of elements, for example, 10. So this would be an array of 10 elements. I want a matrix, so this is an array of arrays. It's a square matrix, so it's an array of n elem multiplied by n elem of integers. And n elem is 10,000, so it's a decently large array. And this is the code you have seen on the slide. And this is the main. Again, the usage, I specify the number of threads. I fill the array. And then I prepare the vector results. I compute the chunk size. And then I compute start and end for each thread. I create the thread. And I just wait for them to terminate. So the results, the partial results are in this vector. So I sum all of them, and I put the result on the screen. So very simple. So now this should work. There is no synchronization, right? So this should go very fast. So count matrix. You want the number of threads. So let's start with one thread only. Okay, so let's actually measure the time. So it takes approximately 2.8 seconds. Now let's try with 2 threads. A little bit less, but not much. Let's try with 3. A little bit less, yes. 4. Wow, more. 5. Less. 6. More. 7. Less. 8. More than 2 seconds. So it's not very nice, right? We are not scaling at all. So now So this is the measure I did before. They are a little bit more uniform, maybe. So the question is why the performance does not scale. So it's a bit puzzling, right? Because it's a very, very simple program. Everything is so simple. So where is the problem in this program? Do you have any idea?
Is it related to caching?
Yes, it's related to caching, but can you describe the problem?
Uh, by using different threads, I'm missing the locality principle, space locality.
So do you know how the cache works, right? Do
Yeah.
you all know how the cache works?
Yeah.
More or less. So do you all know what is a cache line?
Yes.
So cache line is a certain amount of memory which is stored inside the cache. So the cache is organized into cache lines, so basically blocks of memory. So when you want to access one specific location in memory, the entire block to which this location belongs is loaded into the corresponding cache line. So it's not only one single word or one single byte that is stored into the cache, but one entire block of memory. And this block of memory is usually a few words. I mean, not very, very much, but still, it's not one single word. Okay? So, with this information, can you tell me where is the problem here?
Like the cache is invalid every time for different thread.
But what's the specific point of program that invalidates the cache? So when I'm accessing the matrix, I'm accessing the matrix in read-only mode.
Yeah.
So a read does not invalidate the cache, of course.
Okay.
So the problem is on the write. So which one is the instruction that writes in memory?
Increase the result.
Okay. So what happens?
Maybe the result variable is inside the same cache line of some element of the matrix.
Yeah. Okay.
No, actually the problem is different. It's stores all its data consecutively in memory. So since we have maximum 8 threads, all 8 threads probably in the same cache results variable, they all stay in the same cache line. So every time one thread updates the value of results, it invalidates the cache line of the other cores, right? So every core has its own cache. Every core has the vector result stored in the cache. But every time one of the cores updates variable results, all the others caches are invalidated.
Yeah. Okay.
Okay? So they are forced to reload the entire vector in the cache. And of course, very soon they will update again this variable and invalidate for the others. So
Sì, sì. Sì, no, la pensavo. Dipende anche il livello di cache. Sta meno verso.
are you still there?
Yeah.
Yes.
Okay.
Now, yes.
Yes.
So the network went down and then we are still there. So as I said, when you have one single thread, you have one single thread running on one core, and since the cache is a weight, it's a write through. So basically, this is not a problem because accessing the results is always done in the cache. When you have more than one thread, instead, this vector is in different caches. And so every time somebody updates one of the elements of the vector is invalidated on the other caches. And so you have to read again the entire cache line. So it's basically like I don't have any cache as far as result is concerned. Okay?
Yeah.
So how can we solve this? Do you have proposals?
Necessarily. Master result is in different space in memory for every.
No, one thing we could do is to
A local variable.
we increment the temporary variable, and we write the single cache miss at the very end. Okay? Now let's see if it scales. So this is again 1, so approximately 2 seconds. And let's see with 8. Well, it's much, it's the same, sorry. Okay, so I probably did something wrong somewhere else. But anyway, if done well, this should work, okay? So I think I did some error somewhere, but I don't know where. Probably it's so local variable should work right before. Still doesn't work. Probably the matrix is not so big and things like that. But in general, it should work. Okay, so the false sharing on the cache is actually a well-known problem. It has been described many years ago by this article on Dr. Job journal, which is a famous journal online for programmers. It's not so much popular today. Has been superseded by the use of internet, but it's a well-known problem. And probably in my case, it depends on the fact that I'm not running on full power, so it's an hardware thing. So it was showing that the performance was not scaling, and just by changing and using a temporary instead, it was going to work. So in general, I think it should work. Probably I can make sure there are different cache line if I make it much larger. So let's try a different thing. Let's try. Here, instead of using this, I'm going to use this. Okay? So I'm going to put them in different kinds of cache lines for sure. So basically, I'm passing. Result is now much larger, so it doesn't fit all of it into a cache line, and I'm passing just one reference to the element every 100 elements. Okay, and then when I accumulate, it should be basically the same. Let's see if now it works a little bit better. Yes, now it scales a little bit better. Not very much, but okay. Okay, so false sharing, it means that you have to be very careful about where you put your data. But in general, it's very difficult to program parallel programming like that. So to go fast is not easy at all. And as a very general rule of thumb, synchronization is an heavy thing. So if you go back to your previous program, here we are doing a certain and how heavy is this synchronization with respect to the. So if you have to do a lot of work with respect to the then this kind of approach is okay. Otherwise, it doesn't work very well because parallelization. As you know, there is one very famous programming law that is called Amdahl. Is the maximum expected improvement to an overall system. Only part of the system is improved. It's often used in parallel computing to predict the theoretical maximum speed up using multiple processors. Okay, so so the rule is that it depends on the synchronization on the parallel portion. So how much is the parallel portion with respect to the sequential portion, and how much is the synchronization with respect to the amount of parallel work you have to do? But depending on this, you can have more or less speed up. Okay, so this here we have a logarithmic scale, and here you have the amount of speed up with respect to the amount of parallel work compared to the sequential work you have to do. Okay, so total amount of work, so sorry, parallel portion divided total amount of work, this gives you the speed up. Okay, so for example, if 95% of the program can be parallelized, the theoretical maximum speed up using parallel computing would be 20 times as shown in the diagram, no matter how many processors are used. Okay, so you have to know that there is a limit in the amount of parallelization you can achieve. Okay, there is another law, quite important, which is called Gustafsson law, which is very similar. It has to do with parallelization as well. So it's very similar to the Amda law. It's again has to do with how much you can parallelize a code. Okay, so P here is the number of processor. S is the speed up you are going to obtain for that amount of processor, and alpha is the amount of non-parallelizable fraction of any parallel process. So it's very similar to the Amda law. Okay, and the diagram in which it shows how the law is going with respect to the number of processor and the speed. Okay, we have a break, and then we do the last part of the parallel programming part. Let's have 10 minutes break.
Professor,
Yes.
regarding the assignment, one
Yes.
problem is about the hiding node problem. But how to detect the hiding node problem? When I receive or when two nodes they send at the same time?
And of course, the node doesn't know anything. So it's not the node that has to understand if there is a hidden node or not.
Yes.
So you have to devise a class in your code that takes care of checking interference at the global level. So the way to organize the code that somewhere you have to have a class or an object that decides if there is an interference or not in a certain point in the space. Okay?
Okay, but I want to detect it when I receive it, because if the node receive a packet and maybe he has delayed for some seconds to wait, if he during this time interval, if another packet arrives, then the node can say, now I'm suffering from the hidden node problem.
Yes. So what I suggest to do is that you have something called network interface.
Yes.
Where you are going to put the messages that are going to be received. Now, reception takes time. So you have to think about dividing receptions into two different events. Start reception and end of reception. Now, the idea is that if you have two events of start reception on the same interface, then there is a collision. So suppose, for example, that one node starts transmitting. So it's going to put an event of start reception in all the network interfaces of the nodes that are in the range.
Yes.
Okay?
Yes.
Then maybe another node later on wants to send data, and so it will put a start reception in all the network interfaces of the nodes that are in the range. Now, if there is one network interface that is in the range of both, that network interface will suffer a collision.
Yes. But you mean here is that broadcasting. If I send a message, then all the nodes inside my range will receive it.
Yes.
Or if so, in the implementation for the XS1, build the basic model. Then we are using the broadcasting. If a node want to send,
yes.
all the nodes
Yes,
inside
yes.
the range should receive.
No. You always use broadcasting. You have no way of using anything else than broadcasting. So at the MAC layer, you have
Yes.
to use broadcasting. At the upper layer, you discard the packets that are not for you. So the network layer, the MAC layer,
Yes.
where the network interfaces acts,
Yes.
it will always receive all packets in the range. And then, if the packet is not for me, I will discard it.
Receive. But in the second assignment, you said the packet is only sent to the next on the below or on the right. So if I send a
means that higher level. So higher level inside the packet, you have to divide the packet into different fields. One of the field is destination, and the other field is a source, right? So I want to send the packet only to the node which is, for example, in the south. It means I write in the packet as destination, intermediate destination, the packet that is at the south. And but at the lower level, the MAC layer, I'm still broadcasting.
So all the
network
others
interface, as all network interface in the range will receive, after reception, they will look into the destination field and discard all packets that are not for this particular node.
Okay.
Okay, so this is exactly how it works in practice. In practice, this is how it's going to work. In wireless protocol, all network interfaces receive because it's always broadcast. If we are looking in the same channel, of course. If everybody is hearing in the same channel, everybody receives packets in broadcast mode. Everybody. Then, if the packet is not for me, I'm going to discard it right away. Otherwise, I will keep it.
Yes. So in the assignment,
but
you
there
said
is no way of.
Okay. Understand. And in the assignment about communication range is like if they are not in the same, if for all the nodes in the same communication range, so they should share like the link object. And for different communication range, so they share the different links, right?
Yes, so if they are very far and the two communication range do not overlap, there is no collision at all between them.
Okay, so I can develop, build different links for this different communication range.
Yes, or you can build one single link that understands when there is a collision or not. So it's up to you. It depends on how you want to structure. So you think about it, you make a design. So this exercise is also about, it's a complete exercise because it's not just something, write a class and that's it. You have also to decide which class to write and how to structure your code. So you can decide to have one single global network link that understands if there is interference or not. Or you can decide to have several network links connected to each other in some way.
Okay.
So it's up to you.
Okay. Okay. Thank you.
So I suggest to all of you to
Yes.
spend some time thinking about the structure of the classes before actually going to implement. Okay? So I
Okay.
don't know, use your pen and paper, do some little drawings, or write a small portion of codes or things like that, just to understand how to structure the code. And then you start writing. And maybe when you write, you understand that your initial design was not so good, so you have to change and so on. But this is a good exercise for you to understand how to design a large uh, program. It's not very large, actually, but it's a little bit challenging because you have to understand how to relate the classes to each other.
Okay. Okay.
Okay?
Okay. Thank you.
You're welcome.
lo standard error è un po' la mia architettura nuova, però tipo la vita, a livello di pubblicità, o qualità bassa, messaggio che ti viene sparato come fare, sì, magari per il
va a finire in un'obbligata.
sì, resta nel limbo. No, all'inizio non è stato direttamente sul client, è ricopiato tutte le volte, poi ti succede panic, tutto è proprio difficile. Sì, ma siccome per me è comunque tutta la vostra roba, lo so, non sapevo quante cose si potessero fare con un modulo e quante si potessero fare con
Ovviamente quello
mi sembra di sì. Cioè alla fine il mio obiettivo sarebbe quello di crearmi il sound remixare.
sì, diciamo, in realtà un po', però sì, diciamo, io uso ovviamente.
Cioè tipo qui nel cartello rock c'è sono rock, c'ho varia roba. E questo, cioè, ho fatto il cut su SCAD per fare il news inoltre. E mi dà varie informazioni sulla schedularità, cioè su tempi di esecuzione, schedularità, fine schedulazione. E il mio obiettivo sarebbe fare tipo questi, simili. E quando lo invoco mi dice ok, questo task in tempi di esecuzione. Modulino
Quello fa di testa un po'.
sì, cioè è di sequenziale.
Sì. Quindi te dovresti andare a scrivere su.
C'è stato il codice del modulo, dentro init modulo e clean modulo. Qui ecco si chiamano JProbe o JProbe. Questo sono il JProbe perché diranno anche parametri passati dalla canzone invece di JProbe. Quindi dico, queste sono le strutture che mando a JProbe. Questo è il nome della funzione che dice svegliami quando questa funzione viene invocata. Svegliami e invoca questa funzione. E praticamente sulla stessa funzione, perché queste sono queste funzioni che invoco. Queste qui. E se ci fai caso, indicate. E la chiamo quando viene invocata questa è il soggetto del kernel. Kernel scad data. E per i parametri sono gli stessi.
Sì, sì.
Però per fare questo devo fare una cosa un po' più diversa che è includere i soggetti che non stanno dentro gli header classici. Quindi è una cosa un po' non pulito, però è grazie, devo fare così. E nulla, ora devo tirare fuori 5 robe
A fare questa valutazione.
sì, ma intanto questo monitor mi servirà a leggere i parametri. E se no alla fine devo calcolare a mano facendo, leggendo sempre lo scheda a livello utente. Quindi devo parsare il file, devo farmi i calcoli e parsarlo periodicamente.
Ok.
Questa è la cosa periodica su Linux.
Sì, sì. Sì, sì. No, è così più scrivere il fisico. Per far
Sì, mostrando un modello di cose, con tanto già diverso, è persiste. È molato, non so se c'è una perché calcolo tipo mi ci è voluto 4 giorni per come creare l'interfaccia di questo. Cazzo di cazzo. Era per me, un giorno da fare questa roba.
Okay, let's continue. So I did some little modification to the program that was not working before, and I'm including from the computation the time fulfill the array, because it actually takes most of the time. So I'm measuring the time between the start of the computation here and the end of the computation there. And I'm using a simple vector without any special spacing, and I'm using a temporary variable here. Okay, so it seems that on this computer, if you do like this, and you execute with one single thread, I also made the matrix a little bit larger. So the actual time, computation time, is about 490,000 microseconds, so basically half a second. If I do with two threads is going to take actually the same, right? So there is a lot of variability, and well, yes, before it was taking much more. So it's very difficult to make it run well. So we avoid the default sharing, but there is still something that I cannot understand on the cache that doesn't make it work. The problem is that also I'm not in the best condition because this is a laptop, and the charger is not perfect, so there is some problem with this hardware. So I will try to make more experiments and fill the table in a more scientific way in next week, so I can bring you some more scientifically better experiments. Okay, but anyway, let's look at the last part of this course for what concern parallel programming. And so there is one section of the library which we didn't do yet, and which is basically related to asynchronous function calls in C++. So C++ gives you the possibility to execute a function in a different thread. And you can do that by hand. For example, by creating a thread and passing a function, and that's it. The problem is that passing back results is not always very easy. So C++ gives you the possibility of passing back the values by using one library object called future. So what is a future? A future is an object that contains the result of the computation when it is going to be ready, of course. So the idea is that you launch a function asynchronously. That means that the function is going to be executed in a thread. And you obtain immediately an object that is called future. This object eventually will contain the result. Now, of course, it will contain the results only when the function finishes executing. And I just launched the function, so the function has not finished yet. So I can continue executing. The function will continue executing in parallel, And when I need the result, I go take this future and I try to obtain the value. If the function has already finished, I get the value. Otherwise, I block waiting for the function to finish. So it's a sort of a producer-consumer, but everything done on the fly. So let's see how does it work. There is a function called async that is used for launching asynchronous code in C++. Asynchronous code can mean two different things. It can mean that I want to run this function in a separate thread, or I want to run this function later on when I really need it, if I need it. In that case, this is called lazy evaluation. Okay? So there are two options. The first one and the second one. And the second one is the most general and takes an argument that is called the launch policy. And the launch policy can be async, that means I'm going to create a thread, or it can be deferred, that means I'm not executing the function now, but I'm going to execute it later when I really need it. Okay? If I can also specify both in OR mode, I can do the OR, logical OR between the two. And what happens is that the actual evaluation, actual behavior is implementation dependent. So it's the implementation that can choose what it wants to do. If you don't specify anything, well, the OR is assumed. So it's the implementation that decides if it wants to parallelize or not. Okay? So async takes a function with its own arguments, or it can take a launch policy, the function to launch, and a list of arguments. And it will return a future. So the future is something that contains the results of this function. Of course, an example is much better than looking at the prototype. So an async call returns a future that is an object that at some point in the future will contain the results of the function. If a thread tries to obtain the value before the function has completed, it blocks. So, for example, this is the parallel sum implemented in this way. Suppose we have a vector of 1,000 integers, all in 10,000 integers initialized to 1, and you want to compute the sum in a parallel way. So you launch parallel sum, and parallel sum will just divide this in two, and if the length is less than 1,000, it just computes the sum. Otherwise, it divides the range into two, and the first half is computed directly. The second half is given to parallel sum mid-end. Okay? And it obtains a handle. This handle is a future. Okay? And later on, I can do return sum plus handle get. Now, the policy is standard launch async. So this is a parallel program because a thread is going to be created which will execute this same function, but only on the second half of the vector. Okay? So we can actually try to execute this. Sorry, I have a problem here. There is Okay, so let's try to compile it. Okay. Sorry about that. I think I have. Yes, I'm still missing one thing. So this is in future. So I have to include future. And accumulate, of course. Okay, so very simple. We didn't see anything, but it works. And let's see if we can understand how many threads we have creating. Okay. Okay, maybe I will just put an integer because otherwise I'll just lose too much time with atomics, so I just put an integer. Hopefully there will not be. So I created 31 threads and for doing this parallel sum, because every time I was dividing, I just creating new threads. Okay, so this is the implementation. So async launches a function asynchronously, so basically in a separate thread. You don't see the thread because it's hidden in the function, and returns a future. And later on, we synchronize on the end of this function with this get. So get returns the value if it's ready, otherwise blocks and waits for the function to terminate. You have to be a little bit careful, because even if your function is a void and you do async, it will anyway return a future on which you can synchronize. Of course, you cannot get anything because the value is void, but you still have to synchronize. So if you write something like this, this will try to synchronize anyway on the future that is returned. But since you are not copying the future in a variable, it will still wait for destructing the future. So basically, this doesn't parallelize anything, because the temporary destructure of f will wait for the future to get completed. Okay, so waits for the termination f. And G does not start until f completes, and also the following instruction will wait for G. So basically, this doesn't parallelize anything. When you call get on a future, you are actually moving out the result from the future. So basically, after calling get, the future becomes invalid. So the future is actually like a mailbox in which get extracts the value, and after you extract, there is nothing in the mailbox anymore. Okay? So basically, to check if the value is still there or not, you must call valid. Valid is a function that returns a bool. If you call get on an invalid future, the behavior is undefined. However, most implementation will throw a future error exception when you call get on an invalid future. Okay, so this is async. It's a nice feature because it puts everything together. You don't see the thread anymore. Okay, you just launch the function and wait for the result into an object called future. But quite easy way to parallelize. Another mechanism, a little bit lower level, it's called packaged task. Packaged task is similar to an async, but it is an object that wraps a function that can be later executed in several ways, as a thread or as a normal function. Okay? And every packaged task, as always, is associated with a future, and you can obtain the future with the function getFuture. Okay? As always, when you create a packaged task, the function is not executed, but only when the operator is called on it. And if instead of executing it, you want to create a thread, you can pass the packaged task to it. It's a little bit strange, but it works. So basically, suppose you have a function that takes two arguments, x and y, and does the power of x elevated to y. And you create a packaged task which basically wraps this function. Okay? Very simple. And then you can obtain the future with task get future. And then you can put this task into a thread with this standard move task. 210 are the two arguments you're passing to f. And you put that into a thread that you call task td. Then you wait for him to finish, task td join. And then you can get the result into the future that you obtained before, result.get. So again, this is a sort of way of removing the overhead of creating a thread by yourself, but it's still not very. I mean, it's not as high level as async, it's not so low level as thread. So it's something in the middle between the async and the thread. And the lowest level way of interacting with the future is by using the so-called promises. So a promise is an object that can be used as a mailbox. and is used internally to implement async function and packaged task. So basically, you create a promise, and from the promise, you can get the corresponding future. And then this is the function body, which is takes as an argument a promise, and just puts the result 9 into the promise. And later on, you just create a thread which executes this function and obtain this promise, of course. And later on, you wait for it to terminate by calling f3.get on the future. So this is actually a little bit more complicated, as you can see, and very rarely I think you are going to use promise directly, because this is the lowest level of interaction between futures and asyncs. Okay, so asyncs are implemented in terms of promise and in terms of packaging task. So these are the 3 levels. Most probably, well, all you need is asyncs. Okay, which are quite easy. You just decide if you want to run it as a thread, or if you want to run it later on when you actually need it, and you obtain the results with the corresponding promise. So everything here is automatic and very easy to be done. Of course, if you want to implement something similar to async, but with some little difference that is better for you, then you can still use one between package and task and promises for implementing your own low-level mechanism. Okay? Okay, so we have seen performance issues. I'm sorry I could not maybe show you the exact functioning of this example. Last thing I'm going to show you is one way to structure the code into different threads of execution by using the concept of active objects. So these are actually some slides I did some year ago. I did not have the time to update, so I'm sorry about that. Active objects. So what is an active object? Suppose you want to design a simple server, and clients send processing requests to the server, and the requests are processed according to their type. So while the server processes, clients should not be blocked, of course. So you want to implement some sort of asynchronous call. The client sends a request to the server and then continues its processing. The server starts processing the requests concurrently with the clients, and when the server completes the request, the result is stored so that it can be read later by the client. So in asynchronous method call, there is only one thread of flow control, the client. The client code can continue only when the function call results. So this is the so-called synchronous call. In an asynchronous method call, as we have just seen, both the client and the object have their own thread of control. So on one side you have the client, on the other side we have the server, and they execute in parallel. When a client calls a method of the object, it is actually sending a message, and after that it can continue its execution. And if you want to get a result, it synchronizes on the future that will contain the result later on. So you call operation and you obtain a future. And later on, you go and ask to the future what kind of result the server has produced. So the active object design pattern decouples method execution from method invocation for an object. Method invocation occurs in the client thread of control. Method execution occurs in the active object thread of control. And design should make this transparent. It should appear as the client is invoking an ordinary synchronous method. Okay, so to solve the latter problem, we apply what is called the proxy pattern. I don't know if you remember the proxy pattern. The proxy pattern basically is an object that wraps the behavior, and you appear like it's a normal object, but behind there is something different. I don't know, a caching policy, or maybe the object is not there, it's remote, or maybe I'm not loading it, I'm loading it later on in a lazy way, and so on. So the components of this active object are a proxy that provides an interface to the client with regular methods, a method request, a hierarchy of classes that models client request. We need one for each public method in the proxy. An activation list that contains the method request object. A scheduler which decides which request must be processed next. A servant which is the one that will process the request. And a future which contains the response. So the proxy has the right interface, is the one that is seen by the client, and it is an ordinary object. However, it does not directly process the requests, but transforms each request into an appropriate method request object, which is inserted into an activation list. And then it also prepares a future, that is an object that will contain the method return value once the processing is complete. The future is initially empty and is returned back to the client. Okay, so basically the proxy is a class with methods. When the client invokes a method, instead of executing the method, it prepares, for example, a packaged task. So an object that is going to be executed later, and obtains a future for it, and returns the future to the client. So the client can continue executing, and later on will synchronize with the future. On the other side, the proxy has prepared this packaged task, and will put this somewhere in an activation list, so that later on the server can decide to execute it concurrently or not. Method request. It is a hierarchy of classes. Each one models one request. So basically, this is the packaged task. Okay. Encodes the method parameters, contains a reference to a future for the response. It may also contain other specific fields. For example, it may contain priority, precondition, and so on. And the proxy creates method requests, inserts them into the activation list according to some policy. For example, you could create a structure in which inside you have one field which is the packaged task that needs to be executed. Another field is the priority. Another field is the client, because maybe you want to identify which client has made the request, and so on. The activation list is a protected object. It's shared between the client's thread and the scheduler thread, and can be implemented using the monitor pattern, so basically mutex and condition variables. The scheduler is a thread that extracts the requests from the activation list and executes them by calling the servant's methods. Okay, so basically the scheduler is the actual thread of the server, which executes the request one after the other. And the processing order can be customized, for example, FIFO or based on priority or whatever. The scheduler can also check the guards on the request. For example, if there is some precondition that must be true before a method can be executed, the scheduler can check this condition, these predicates. Okay? The servant, finally, it's the one that actually implements the object. It's the original object that you wanted to parallelize and make it concurrent. And it's the one where you put the actual method. Okay? It can also implement guard methods that are used by the method request object to understand if a certain method request can be actually processed. So the class diagram is quite complicated. On one side, you have a proxy which implements the operation. So the client will invoke operation on the proxy, and as a result will obtain a future. Okay? The operation here will just produce, instantiate a method request, which contains, for example, methods for checking if the method can be executed, and then a function call for actually executing this method. And you can have several of these methods implemented. The method request is instantiated by the proxy and inserted in an activation list. The activation list is just a queue of objects type method request, which are all the requests made by the client in a certain queue. And finally, you have the scheduler, which is the thread, which just waits for something to be inserted into the activation list, and when this happens, it starts executing it by executing the corresponding operation. Okay? So what happens is that the client calls the operation and gets a future. And later on, according to a certain priority, a certain order, whatever, the servant is executed by calling the corresponding operation. And when this terminates, the result is put into the future, and you obtain the final result. Okay, so how can you implement this? Is by using either a packaged task or a pair of promise and future, right? So the dynamics, I think, I already explained. So the proxy creates a concrete method request. It binds the method parameters. If necessary, creates a future and binds it to the request. It inserts the request into the activation list, and if necessary, returns the reference to the future. The scheduler monitors the activation list. It calls extract in a loop, and it blocks if the queue is empty. When the extract returns the request object, it first checks the condition by calling the guard method, and if the response is true, the scheduler runs by calling method call. Okay, so basically you decouple on one side the client, the other one the scheduler. Okay, so basically, how do you do that? It's better to start by the servant. So you start from the right here by implementing the business code here, and then you can write all the wrapper around to try to wrap all of this so that the client can invoke it asynchronously. Okay, so I think we can skip this because we have already seen more or less everything that is needed. So I wanted just to show this pattern, which is quite famous in the parallel programming practice. Okay, that's it for today. So next week we have last week of lecture, and we are going to do a little bit of software engineering. So we are going to talk about refactoring and agile programming. So the programming part is finished, and we are left with something about software engineering. And for what concerns the project, as I said, I hope to complete the correction by this week, so Monday or maximum Tuesday. I will send emails with the result of the second project, so that we can discuss it next week. Okay?
Okay.
Okay. So thank you for today. Do you have any other question?
No.
Okay, so again, if you still have questions about the project, do not hesitate to ask or to send me an email with your questions. Bye-bye.
Bye.
Thank you.